before we get things started. Okay, so let's actually get the show on the road. We got our big things today are to finish up sockets, and particularly multi-threaded sockets, go over the design for JTalk, which is your third problem you need to do on the homework assignment. And if we have time, start talking about some of the high-level concurrency features in Java. Not sure we'll get to those or not. If we don't, there's no big deal because it really wasn't meaning to get to them until Tuesday anyhow. But not sure I have enough material otherwise. So we'll see whether we get to 3 or not. Before we get started, I can tell from some of the posts on Piazza that there's still a little bit of misunderstanding about what can cause race conditions. So problem 1, you have this timekeeper object. And you can have some contestants. Let's call them contestant 1 to contestant n. And you have a reporter thread. So one of the things you have to do is keep in the timekeeper an array or something for contestant times. And I think some of you have come to the conclusion that as long as I use a vector here, I'm golden, that I can't have any possible problems because vectors are meant to be used with threaded applications and have synchronized methods, okay? So it is certainly the case that a vector can stop you from any issues with a simultaneous access to a particular contestant, okay? But I don't think many of you are seeing the forest. You're just seeing the tree. And you're thinking, okay, the only atomic operation I have here is being able to get something out of the vector or insert it into the vector. Okay, but let's say that contestant 1 is needing to update its record. What you get out of the vector is contestant 1 doesn't have an atomic value in there. Contestant 1 has an object which has some information in it, like say name, maybe time, maybe segments completed. So you end up, contestant 1 is trying to update this, okay? And it got it, and now contestant 1, while it's in the middle of updating this record, it gets interrupted. And now the reporter thread comes in and it's doing its for I equals 1 or 0 to whatever. And it grabs, it does a get from the vector for contestant 1, and what does it have? Something that's in the middle of being updated. So your vector didn't stop the race condition. Okay? So you need, vectors don't obviate the need to potentially have synchronized methods. Okay? You can still, as I just showed you, end up with a race condition on a contestant's object. Okay, same thing. The reporter might be halfway through printing contestants. Like might have gotten through, say, C1 through C4 and is working on C5 when it gets interrupted. And then C5 comes in during the interruption and starts updating its record. And then it gets halfway through the update and gets suspended, and the reporter picks up and it's a mess because now the reporter is getting half of what was there before and half of what just got updated. So vectors alone aren't going to solve your synchronization issues. So if you think or thought that vectors alone were going to solve all your synchronization issues, go back and rethink this problem, because they are not going to solve all of your issues. They're going to solve some of them, but they're not completely solving your synchronization issues for problem 1. And that's why you got that question in number 2, was to make you think about it. And I guarantee you the answer to question 2 is not vectors solved all my synchronization issues, and therefore I did not have to use synchronized methods. It's not that easy. Okay, so questions about that? Anyone? Okay, so basically, again, the idea I'm trying to convey here is not all atomic operations are as granular as a simple insert or read from a vector. Sometimes an operation is a bigger, coarser grained thing that's atomic. Like you may have to have the reporter have complete access to the array while it goes through the entire array, or you could end up with erase conditions. So that whole time where they're going through the loop and accessing the vector, that whole thing, in fact, may be an atomic operation that needs to be synchronized. So what you need to think about is that atomic operations can be fairly significant chunks of code, not just 1 or 2 statements. Okay. So with that said, let's move on and finish our discussion of sockets. And of course, I have the wrong window, so let's get the socket window open. Okay, so first, I'm just going to very quickly review things, just so that we make sure that we're all on the same page. So a socket is a way that 2 independent processes communicate with one another. So threads belong to the same process. They don't have to worry about this communication issue because they're accessing the same memory. Okay, they have to worry about synchronization to avoid stepping on each other's feet, so to speak, but they don't have to worry about communicating back and forth. But if you have 2 independent processes, typically a server and a client, now they're going to have to communicate information back and forth. The way they do that is through sockets. They send messages over sockets. So server side, they listen on what is called a port, and the client tries to connect to that port. When the client issues a connection request, a socket gets generated on each side, and each socket has a read and write stream. So the server can read from the client and write back out to the client. And these read and write streams function just like a file stream or a console stream. Same idea. Okay, so a simple interaction is one where, this was the Echo client, is where the server side is sitting there waiting with the accept command. When a client connects, the accept command returns a socket to the server, which is capable of reading and writing. And it also, on the other end, on the client end, the client gets a socket. which also allows them to read and write. So the Echo client or Echo server that we showed last time was one in which the client, there we go. Client read from standard in, took that standard in and wrote it across the link to the server. The server read it, essentially did no processing. It simply wrote that line back to the client, which read it and wrote it to standard out. So it was a very simple interaction. So then we made it a little more interesting with knock-knock jokes. So there, the server was sending parts of a joke to the client. The client was responding. And when the client responded, some processing had to take place, which was done in the knock-knock protocol object. And based on that processing, the knock-knock protocol object returned a string, which the server then sent to the client. Okay, so that, again, was still fairly simple because we had one server and one client. Where it gets interesting is when we have multiple clients and one server. So what we have now is we're going to have a multi-threaded application. So basically, on the client side, we are going to have to be able to read from standard in, because these are jokes. So we're talking now about the knock-knock server. So each client, in effect, has a different knock-knock repository. So the client is reading from standard in and is writing to a socket. Okay, it is also having to read from the socket and write to standard out based on what it gets back from that socket. Okay. And the server, do I have something from the server? No. Unfortunately, I don't have it on the server. So we're going to have to just walk through. Actually, I can. So the server, so now the server, again, we have a socket server. And again, it's waiting on an accept. But now things change. Before, when it accepted the client's connection, it was able to turn its full attention to the client. It didn't have to deal with any other client. That is no longer the case. When it accepts a connection from the client, it needs to both service that client while continuing to accept connections from other clients. And at all costs, it does not want to waste very much time setting up the connection with the new client, because while it's doing that, it can't accept new connections. So what it wants to do is, as quickly as possible, delegate the task of interacting with the new client to a thread. So what it's going to do is, for each client, it's going to generate a new client thread. And that new client thread is what is going to handle all of the interaction with the client. So it's going to have its own knock-knock object. And it's going to be writing to a client. And that client is going to be, in turn, writing back to this client thread. Meanwhile, this server socket immediately goes back to waiting to accept a connection from another client. So after accepting, it immediately forks a new client thread. That client thread is responsible for all interactions with that client. Okay, so let's take a look at the multi-threaded knock-knock server. And it's like we're going to have to it's amazing. You can't get the doing this search. The third result is the Java tutorial on it. And I am number 4. Look at that. Okay. So we already went over the single threaded. Don't care about the single threaded. We care about the multi-threaded. Okay. So we now have a multi-threaded server. And what it's going to do is this is not what I want. Maybe here's the multi-server. That's what I want to start with. Okay, so the multi-server is going to, as you see here, server socket, create a server socket. And as long as it's listening, essentially it's an infinite loop. It's going to, as you can see, server socket.accept. When that connection is made, it generates a socket. You can see that what we immediately do is fork a thread to handle that client, passing that socket that we got, and we start the thread. And then we immediately go back to listening. So this is like nanoseconds spent generating the connection before we go back to listening. But what's important is during this time, we are not listening. So the reason I'm making such a big point of this is when we get to the JTalk, you may find yourself tempted to do some initial processing for the client in the server. You can't do that unless you're willing to stall all clients that want to subsequently come to your talk server. So you basically write a really tight loop for this accept statement, and everything is done in the thread that supports the client. Okay, so you notice this is a very short program for this server. Okay, because all it's doing is it's getting a port number from the command line argument. So the command line argument is a port number. And as long as it's able to generate a socket on that port, it then just goes into this tight loop. Now, looking at this server thread, this is what is handling the client. So the client, so it's generating a print writer for the printing and a buffered reader to read from the client. And notice it's using a try with resources. Okay, these parentheses, try with resources. So these things will be automatically closed when the try statement exits. That's why you don't see any close statements at the end. It's always good with modern Java to use these try with resource statements. Okay, so then we are, for each client, creating its own knock-knock object for that client, exclusively dedicated to that client. And after that, everything else is exactly like the code you saw on Tuesday for the knock knock client, where we start by sending null to the knock knock object, which gives us an output line that we print to the client. And thereafter, this while loop interacts with the client exactly as it did on Tuesday. So this thread rightly views itself as interacting with a single client. So basically, we moved much of the code that was in the server on Tuesday, and we moved it into this server thread today to handle the multi-threading. If we go back and look at what we did on Tuesday, let's go and look here. So on Tuesday, after we accepted the socket connection, we did all of the work associated with handling the client in the server, okay? Because we didn't have to accept any new connection. So all work was done in the server itself, and we did not fork a thread. Today, we forked a thread and put all of this code here, we put that into a separate thread so that we could put the server into a tight loop on this one statement right there, okay? Now, you have some issues as well with the client. So let me go back, take a quick look. Okay, so also on Tuesday, we had a very simple model for the client interaction. So coming back here, the client you see this? Good. Okay, so the client would read from standard in, it would write something to the server, it would then wait for a response from the server, read it, write it to standard out, and then read again from standard in. So this could all be done in one thread because either the client was blocked waiting from input from standard in, or after it read from standard in, it blocked waiting on a read from the server side, okay, which is the same today with the knock knock, multi-threaded knock knock server. It's still a sequential process where it waits for standard in, gets it, sends it to the server, then waits and on a read from the server's socket, writes it to standard out, and then does a wait on standard in. Okay? Now, when we go to JTalk, this changes. So now we want to transition to a chat application. Okay? And for the time being, we won't worry about chat rooms. We'll just assume it's one chat application. So everyone is put into the same chat room. Now, two things. The client is potentially having to both read from standard in, because I'm sitting there and I might want to contribute to the conversation by typing something. But this client also has to be listening to the socket, because at any time, anyone else, like here in the classroom today, we have 3 people, any one of those 3 may want to talk back. So I'm actually in the situation with the client of potentially having to both read from standard in and read from the socket at the same time. And I can't do both simultaneously. I can, if I'm trying to read from standard in, I block. Anytime I issue a read request, I block. Okay, so if I try to read from standard in, I block. And while I'm blocked, I cannot read from the server socket, and hence I cannot output anyone's chat messages. Conversely, if I decide to read from the socket, I will not be able, I will again block until someone chats. And I will not be able to enter any new input. So this is a case of the client cannot be in 2 places at once. This was not a problem with the knock-knock server. With the knock-knock server, the client was either reading from standard in or was reading from the socket, but it was sequential. That's not the case here. Here, you must be capable of reading either from standard in or from the socket. And we can't do both in one thread, it turns out, because as soon as we attempt to do a read, we will block. And we can't do a read and a timeout. That doesn't work. Once we start reading, we're stuck, we're blocked. So the only way we can simultaneously listen to 2 different read streams is by forking a thread. It's basically, we have 2 threads. One is listening to standard in, one thread's listening to standard in, one thread is listening on the socket. So when you do your chat application, your JTalk, the client is going to have to fork a separate thread. And my suggestion is that that separate thread read from the socket, while the original thread, which is main, be the one that is reading from standard in. But it doesn't matter which way you do it. You can do it either way you want. Here I have the main thread that has main, reading from standard in and writing to the client. And I have the other thread reading from the socket and writing out to standard out. Okay. So the way that looks in the client, this is pseudocode, in the main thread, that is the one that has the main procedure, the first thing you're going to do is get a new socket. That's where you establish the connection with the server. You get your socket read and socket write objects. That's where you create the buffered reader and the print writer. Then you create this thread that's going to write other people's chat messages to the console. And you're going to pass to its constructor the socket read object that you created, because that write console thread needs to be able to read users' chat messages from the server socket. Then the main loop, having done its setup, goes into its processing loop, which is while there's more standard in, it writes that chat message to the server. Meanwhile, while it's sitting here waiting on standard in, the write console thread is able to run, and it's sitting there waiting for input from the server socket. So whenever someone else writes a message to the chat room. That message will be broadcast by the server socket, and I will receive it, process the line, and write it to the console. Okay. Questions about this? Does this make sense? Okay. Now, there is an issue of detecting shutdowns from either the client or the server. Because the server shuts down, you don't want to be sitting there endlessly waiting for something to happen if possible. And similarly, so you want to be able to shut down the client, okay, and cause the program to exit. So the way you shut down the client is when the socket read object returns null. So that's how the client detects that the server has shut down. You might think that the server calling its close method would send out a signal saying I've terminated. It doesn't, and I'm not really sure why. So closing the socket on the server side does not broadcast any issue. But fortunately, as soon as it closes, essentially on the read stream, it will put a null onto the read stream. And that means that the client will pretty much simultaneously with the closing of the socket receive a null message from the server, and it can act on that. Okay, so the way it does that is in the console thread. If it receives a null line from the server, it knows that things are ready to shut down. But it has to communicate that information back to the main thread. The main thread has to be told that the program can exit. The way I suggest you do that is by introducing a Boolean variable. I called it interrupted. And when you come out of the while loop in your write console thread, set that interrupted flag to be true right here. Okay, now your write console thread will exit. Okay, and you come back here, and there's no way to actually stop to cause the program to the client to shut down immediately. While it's blocked on standard in, it can't be interrupted. At least I don't know how to do it. And I know that I searched. So I think you're pretty much stuck waiting for user input here. I don't think, well, I think what could be done is that you could certainly write a message to the console saying server has shut down. And that would be a pretty clear indication to the client, to the person looking at the screen, that nothing's happening anymore. But you probably have to write that line to the console to let the person know, hey, the server's gone down. So they can then hit essentially return to cause a line of standard in to be read. As soon as something is read from standard in, you can then check this interrupted flag, see it's been set, and break out of the loop. Breaking out of the loop causes you then to essentially exit main, and the program shuts down. Okay? This is important because if you don't do this, the client will hang. And I want you to cleanly shut down your program. Why am I showing you this? It seems simple because this used to be a huge problem on this assignment, and I wasn't actually shutting down properly. It took me a couple hours to figure out how to do it. It's not simple. I'm giving you a nice, simple solution. So make sure you remember when you're writing the assignment to come back to these slides, because this is a rather delicate handshake situation. Okay, now coming back, it's a lot easier on the server thread. So The server thread can exit anytime it darn well pleases. But if it gets something from the client, it's pretty easy. It gets a null from the client. The thread that is servicing that client will simply exit the while loop, wrap up, and terminate. That won't shut down the server. That will just shut down the one thread dedicated to that one client. Okay. So normally the server wants to stay up. It normally does not want to terminate when a client exits. So that's the case where chopping off one branch shouldn't kill the entire tree. Okay. So questions about any of this? Okay. So now let's talk a little bit about the design of your JTalk program because it's a little more complicated. Okay. So let's first just do a little example. So remember, if you're doing this on the Hydra machines, if you set up your server on the Hydra machines, then it's not, you're going to have to do all your interaction on the Hydra machines. You can't remotely connect to the Hydra machines because there's a firewall. What I am going to do is do it all locally just to make my life easy. So okay. So we're going to start, we're going to boot up first the chat server, and we'll make it port 10,000, and we will give it the topics of football, bridge, which is something Dr. Plank and I both share an interest in, and politics. Really? Because I didn't say Java jar. There we go. Okay, so we've got it set up on 10. Now, I'm going to have to create new window. Okay, so I'm going to create two. I'm going to create two participants to chat. So I do Java jar talk client, and we're connecting on the local host and port 10,000 BVZ. Thank you. Talk client.jar. Okay, so what immediately happens is the server broadcasts the available chat rooms, which are bridge, football, and politics. And it broadcasts who's in each room, which I'm the first person, so no one's in any of the rooms. So I'm going to first enter an invalid room. I want to talk about soccer, and it doesn't like that because it's not one of the valid rooms, so it just, again, says enter a chat room. So I'm going to enter the bridge. It says BVZ has joined. Okay, is anyone here? So you see it broadcast my message, but of course no one else is here, so right now crickets. But let's have another person join. And we'll name them Goofus. And what did I not give it? A host name, localhost. Okay, now you see that BVZ is in the bridge room. Also, by the way, notice it's in sorted order. Okay, it's not in the order they were presented. In the command line arguments, it's in sorted order. But these people are in the order that they entered. So I'm going to enter the bridge chat room. So now you noticed up here, BVZ also sees that Goofus has joined. So it got broadcast to every chat room. So Goofus says, hello, Dr. Brad. And you see it's echoed both here and in Goofus's own thing. Hi, Goofus, how goes? Okay, and now it, let's see, Goofus, sorry, gotta run. And now I hit Control up here. I'm going to get out of here by hitting Control C. And you'll notice that killed the client program. Here it did not. It just says BVZ has left. But down here, Goofus is still, I'm still alive. Okay, and we will boot something else. So now we'll have Dr. Plank enter. And you'll see Goofus is still there. So, hi Goofus, sorry that Dr. BVZ was such a rush. And you can see we're down here, it's all good. Goofus says it's all good. Now I'm leaving. Goofus takes off. Goofus is left, but Dr. Plank is still up. Okay, so that gives you a feel for the interactions. Okay, and I know I just used 2 individuals, but these chat rooms can have an arbitrary number of individuals in them. There's no upper limit. So the important things are you have to keep the chat rooms in sorted order so that when a user comes in, so we'll bring Goofus back in. So the first thing that has to happen is that the server needs to broadcast the chat rooms to the client and the list of people in those chat rooms. Then the client needs to propose a chat room, which will be sent back to the server. The server will either accept it or decline it based on whether you chose an existing chat room or not, and then establish a connection if there is. So basically, your sequence of actions is the client connects to server, then the server, so actually maybe we'll have client and server. So client connects to server. Then the server accepts connection. Forks a helper thread that is the client helper thread. And the helper thread sends chat room information to the client. Now the client prints chat room info. And asks for selection. Okay, then the client sends chat room to server, helper thread. Okay, if a valid chat room then broadcasts the new participant to all chat rooms. I'm sorry, to all people in the chat room. And from then on, the client can does two things. Listens. So that's the setup. And then thereafter, I'm not going to go through it. It's what you saw. The client is listening to standard in, and when it gets a line, it sends it to the server. And it's simultaneously listening to that socket with the server. And when it reads a line, when it gets a line from one of the other chat participants, it prints it to the console. Okay. Now, the important thing, as I said, is that the helper thread is the one that is dealing with sending the chat room information to the client, not the main thread. The main thread is in a tight loop accepting connections. Okay, and then in my write-up, quick look at my write-up. Okay, so how did I set up the chat rooms? What I did is I created a chat data object. Okay, so the chat data object was the object for a chat room. There was one chat data object per chat room. I suppose I could have named it chat room. Okay, and I gave it 4 methods. You're free to do anything you want in how you design the API. I'm just telling you what I did. So I had a distribute message method that distributed a method to all clients in the chat room. So basically went through all the client sockets and wrote that message to their socket. I had an add client method that added a client socket to this room's list of participants. Okay, it's a simple list. Delete client removes that client socket from the list. So you might, I actually used a class to keep track of a client because I didn't just want their socket information. I also needed their name, and it helped to have a print writer for the socket. So I actually used a class for each client. So I was actually adding a class containing information about the client. And then finally, this broadcast members was a way to write a list of the chat room users to a new client so that the client could display that list. So as I said, you're free to do it any way you want. I just, I know it's a complicated assignment, so I tried to give you a flavor of how I designed it. And for those of you who have implemented JTalk in 360, I have occasionally noted where there's differences, because I know that there's a few subtle differences between the implementation you had to use with POSIX threads and the implementation that you'll be using with Java threads. Any questions about this? We're all good or overwhelmed or hopefully understanding? Okay. So just remember that I broke this assignment into two parts. So the first part is actually due tomorrow night effectively. And then the talk part is not due until essentially next Friday. So feel free to ask questions about it on Piazza or in office hours, or on Tuesday or Thursday of next week. Okay. So I do have a few minutes. And because I have a few minutes, and because actually I think the high level Java takes a bit of time to cover, I am going to start into that today. Okay, so I've never looked at the design documents for Java, but my guess is that when Java was first designed, they basically looked at the C thread libraries and said, we want something a little higher level than that. And concurrency is too difficult. It's hard to write monitors. We're going to try to simplify writing mutexes and monitors by using synchronized methods. And that's going to be a lot easier than having to write these guarded monitors using POSIX threads. So they developed their concurrency framework, and as much as possible, they hid the notion of locking from users because it's a difficult concept. But what they discovered is that if you don't give the user some control over the locking mechanism, you can easily get deadlock, which is what I showed you on Tuesday, where Gaston and Alphonse were trying to compute the outcome of a contest between the two of them, and they deadlocked. So Java tried to make concurrency easy by saying, okay, we're not going to really make locks explicit, just like we're not making pointers explicit. But the trade-off is that by not making them explicit, you can't do things like back out of a lock. It's a irreversible. Once you ask for a resource, you're stuck. You can't back out of that request. And unfortunately, that makes synchronization and avoiding deadlock somewhat difficult to do. So they realized that they needed to add locks that users could control. So they did that relatively soon after the introduction of Java. And then they did a few other things as well. So they introduced the notion of thread pools, which are called executors here. And thread pools were introduced to deal with the problem of multi-cores. So at some point, Moore's law became obsolete, and they couldn't really get any more performance by doubling the speed of single CPU machines. And therefore, most laptops these days and desktops come with multi-cores. Well, trying to schedule threads on multi-core machines is not something you really want to the programmer to do. So Java introduced the notion of thread pools, where basically you said, I have a thread, I'm forking it, I'm putting it in this pool, you figure out which core to schedule it on, doing it in the most efficient way possible. So we're going to put off a discussion of executors and thread pools until Tuesday, because that really is a big topic. Then they introduced the idea of atomic variables like counters and arrays of variables that you could do simple operations on, like increment or decrement. Those were atomic variables. Then they said, okay, our objects, our generic objects that we have now in java.util aren't suited for threads. So array lists don't work with threads. A whole bunch of other things don't work with threads. So we need to introduce hardened versions of these collections that work with threads, and they did so. So for example, vectors were introduced, and vectors are essentially like array lists, but vectors work with threaded applications. So basically, these concurrent collections introduced atomic operations for things like insert, delete, and the like. And then they introduced random number generation. Now, I am forcing you all to do that yourselves in homework 8 by only allowing you to allocate one instance of a random number generator. And as I'm sure you will feel by the time you're done doing it, it's a royal pain in the neck. Okay, so Java rightfully said, okay, often threads need to do random number generation, and you shouldn't have to do all of this generation by using explicitly synchronizing the actions on that random number generator. Instead, we're just going to give you one that can be shared among multiple threads without your having to do something with it. So we'll start out with the MutexLocks, and we may or may not finish them today, but at least we can get started. So all of these new inventions come from the java.util.concurrent library. So you have to import from java.util.concurrent. So the first thing they introduced, I believe this was in Java version 7, was a new lock interface. And the principal methods that it supports are locks. So you can acquire a lock, and if the lock's not available, you will sleep until the lock becomes available. If you don't want to unconditionally acquire the lock and sleep, which is what happens with a synchronized method or a synchronized statement, instead you can call the try lock method, which will try to acquire the lock, and if it fails, it will either give you a true or false. So either you get it and it returns true, or it fails and it returns false. But either way, you are free to immediately proceed. Okay, you're not, if the lock's not available, you're not stuck. You can also give an argument that says, I'm willing to wait this many milliseconds to acquire the lock. So I'm willing to sleep for this amount of time. And if I can get the lock within that amount of time, great. And if not, it times out and it returns false. Okay, so which is a good way to avoid deadlock, because you only end up waiting for X amount of time and you realize, well, this isn't happening. I can either exit or I can try something else. Okay, unlock releases the lock. This one is lock interruptibility, says that I want to acquire the lock, and I am willing to be interrupted while I wait for that lock. So I want to basically go to sleep, and I'm willing to wait as long as I need to get the lock. But if someone detects deadlock and I'm the source of the deadlock, I'm willing to be awakened and interrupted and told essentially do something because you're causing a deadlock situation. So that's what lock interruptibly means, is that I'm going to sleep until I get the lock, but I'm willing to be interrupted and told essentially something's amiss and you need to react to it. Okay, and I won't get the lock in that case either. So also, you want the ability to wait on a resource until it's available, and or if there's too much of that resource, or if you have provided a resource, then you want a way to indicate that that resource has been provided. So producer-consumer problem. And the way that's handled is you can call this new condition method, and it returns a condition object. You can't actually, as far as I know, associate a condition with it. Instead, it has two methods that act like wait and notify. So await will cause you to wait until some other thread issues a signal for this block. And then .signal is the way that another method can notify other threads that some condition is fulfilled. So maybe, for example, you have added something to a queue. So in fact, let's take a look at such an example. It's the bounded buffer example, and see how that works. Okay, so basically what we want to do is the classic producer-consumer problem. We have a buffer and it contains up to 100 items. So if the buffer is full, the producer needs to wait until there's an empty one. If the buffer is empty, the consumer needs to wait until someone has put something in it. So here, remember, lock is an interface. It's not a class. So the most typical concrete class that we use is reentrant lock. Okay, remember, reentrant means that any method, and with synchronized methods, it meant that any, if you held the lock for an object, you were allowed to call any synchronized method in that object. So it's kind of the same idea here. So we create a new instance of a reentrant lock, and then we create two condition objects, one to indicate that the buffer is not full, and one to indicate that the buffer is not empty. Okay. So notice no synchronized methods. We're not using synchronized methods. So put is supposed to put something into the queue. So it goes and it locks the lock, meaning it's willing to wait indefinitely until it gets the lock. Then, while the count is equal to the items.length, so basically if the buffer is currently full, we call not full.await. So we want to wait until the not full condition is fulfilled. When it is, we assume that put pointer points to a free slot, we add our item to that free slot, and if necessary, we wrap around. So this is a circular buffer. And we add 1 to the count, and then we signal that it is not empty. Now, it might not have been empty anyhow, but regardless of whether or not it was empty before, we signal that it's not empty. And finally, we do the unlock. Notice here we are not doing a try with resources. We are using the finally statement to unlock the lock when we are done. So no matter what happens, because notice we might be interrupted. So no matter what, if we get an interrupt, we better unlock the lock. No one's doing it for us. The synchronized methods automatically unlocked as they came out. But these locks don't. If we forget to unlock them, they remain locked, probably causing deadlock. So we have to explicitly unlock no matter what, hence the finally statement. Okay, and then take, it's taking something from the buffer, so it gets the lock while the count is 0. So if it gets the lock, but the buffer is empty, it releases the lock by calling wait. And when it finally, so when the not empty gets signaled right here, it now awakens. Now, it can't just assume that the count is greater than 1 because some other consumer might have snuck in and grabbed the resource. So it, even after awakening, it still checks to see that the count is not 0. And when it's not, it grabs the item, indicates that this item, it basically increments the take pointer to indicate that the item has been removed from the front of the queue. It wraps around if necessary, decrements the count, and no matter what, unconditionally signals that we are not full. And then just like the producer, it has a finally statement that guarantees that it is unlocked, that the lock is unlocked when we're done. Okay, so that's a pretty simple example of using locks to do the producer-consumer problem. Now, a couple things. First of all, it could be done without using these locks. They're just trying to show you how to do it. And secondly, there is already a class called array blocking queue that provides this functionality. They were just doing it as an example to show you how to use the lock and the condition objects. So questions about that? Okay, so the big thing to notice is there were no synchronized methods here. This was all done without using synchronized methods. But the other thing to note is there was a lot more code devoted to ensuring that the synchronization worked. It was a lot simpler when we did the original producer-consumer problem. So if we look at the Dropbox for a moment, let's see, or was there, it was here, but maybe not. Maybe here. Yep. So it was a lot simpler. This was the producer-consumer problem we did before. It was a lot simpler. It just wait, try, wait. There was no basically you just said while empty, try, wait, catch interrupted exception. And for the producer, again, while not empty, try, wait. It was a lot simpler. So the reentrant locks give you a lot more control over things, but your code's going to be longer and more error prone. So it is a trade-off. Okay, so I'll give you another example of MutexLocks on Tuesday. Let me just quickly skip down. There we go. So concurrent collections, you are probably using one in the current lab. Vector is one of them. So the things like array lists that aren't thread safe, try to do something called fail fast if a concurrent modification is attempted. Okay, so if they detect that two threads are trying to access the same part of the same list simultaneously, they will try to fail fast by throwing some kind of exception. But all they guarantee is best effort. They don't guarantee they will detect it. So that's why they introduced synchronized classes, because things like insert and get and find typically need to be atomic operations. So the blocking queue, you just saw that. Well, you saw how it's probably implemented. There is a concurrent map class, which is good for hash tables, and a concurrent navigable map, which is good for sorted maps, and a vector, which is good for array lists. So that is good to know about. Just thinking for a moment. I know that in my JTalk program, I used a map. I don't remember whether and I know I used a sorted map. I don't remember whether I made it concurrent or not. I'd have to think about that. Okay, but at any rate, the synchronized classes, they are designed to work with multi-threaded operations. They make certain operations, particularly find, insert, and delete, they make them atomic. But as I discussed at the beginning of class, don't think that that necessarily eliminates race conditions. As I showed you at the beginning of class, the vector was storing an object. That object could be, you might be in the middle of modifying that object, which was not protected. Okay, unlike the vector, which was, the contestant object was not protected, and therefore you could be halfway through modifying that object when you got interrupted. So these things aren't, they don't eliminate the need for synchronized methods. They just simplify things. Okay, and then you're not allowed to use this for your own homework assignment, but Java 7 introduced the thread local random, which basically was a random number generator that was internally seeded, which is a bit of an issue because you can't reproduce the behavior in that case. But it was a way to avoid sharing intention with math.random. So right now, I'm making you all kind of create one instance of a random number generator. So that's one way to do it. Basically, math.random wasn't meant to be used in a concurrent setting. So if one thread seeds it to 10, and then another thread comes in and seeds it to 50, things are going to get messed up. Okay, so it wasn't meant to be shared. So Java introduced its own random number generator to handle it, but your trade-off is you're not allowed to seed it because essentially it's shared. Okay, so it's faster than generating your own random number generator objects. And the nice thing is you can actually specify ranges like this, which you can't do with random. So in the second, or in the homework assignment, you need to generate a number between 1 and 8, or 1,000 and 8,000, but you can't. You actually have to generate a number between 0 and 7,000 and then add 1,000. But here, you can generate numbers in any range that you want. Okay. So you call thread local random dot current. So that gets the random number generator in effect for the current thread. Next X gets you the next value. So it handles all the contention issues that you might otherwise have. Again, you cannot use this for the current homework assignment. Okay, so Tuesday, we will give you another example of mutex, basically MutexLocks. And then we will spend most of the lecture on Tuesday talking about thread pools and all the ways that you can control them. So with that, I will wish you all a very nice weekend. The sun has come out here finally after a rainy day. So I hope you all enjoy it, and I will see you on Tuesday.